This video is a electrochemistry diploma prep video, but it'll also work as a test prep if you're just doing this as a unit test in Chemistry 30, which is in the province of Alberta. The concepts would apply to students in other provinces, but the language and the exact outcomes are for Alberta. So this is the breakdown for a diploma exam in Alberta. The electrochem section or weighting of electrochem is going to be a little under 1/3. So the diploma exam will have a total of 60 questions. So you're going to see about 18 of those questions being electrochem or redox. Now we don't know exactly how many will be multiple choice or numeric response. The diploma will have 44 multiple choice in total, and the remaining 16 is numeric response. A lot of comments in this video series will relate to the 18 total questions on a diploma. If you're studying for a unit test, you'd want to kind of just scale that up. Maybe there's about double the amount of questions on a unit test, so twice the count compared to a diploma exam. So this video is going to be split into 4 parts. The first general outcome explores the nature of redox reactions. And I'm going to just go through sort of oxidation, reduction, and key terms in the first video. In the second video, I'll finish up general outcome 1 relating to building reduction tables and ending with titrations. The second part of the redox unit, or general outcome 2, is applying your knowledge to electrochemical cells, be it voltaic cells or electrolytic cells. So again, I'll break this into 2 separate videos. Part 3 being on intro terms like anode, cathode, salt bridge, and the second part more on the cell potential, which would more commonly call it voltage in everyday language, but electric cell potential is the technical term. So we're going to continue on in this video on part 1 and look for the following videos for part 2, 3, and 4. So the first outcome is identifying oxidation and reduction. You're never going to get a question that asks you to define them in words. It'll always be an application. So I've got 3 examples to take a look at. The first example is this aluminum and chlorine redox reaction, and you could be asked to figure out what is being oxidized and what's being reduced, and your strategy would be to use oxidation numbers. So we have aluminum in its elemental form. So anything in its elemental form has an oxidation state of 0. It doesn't matter if it comes in 1s or 2s or 3s. We've got chlorine also in its elemental form, happens to come in pairs, doesn't affect the oxidation state. So we have 2 elemental forms, oxidation states of 0, and it becomes an ionic compound. So we have aluminum 3+, and we have chloride 1-. Charges are balanced because there's 3 total chlorides to become -3 in total to balance the +3 of the aluminum. So we want to figure out what's going on with these oxidation states to figure out if electrons are being gained or lost. So if we look at the aluminum is going from 0 up to +3. So the aluminum is losing 3 electrons to become the 3+. So losing electrons oxidized. So the aluminum is being oxidized in this case. Now there's several mnemonics to help remember oxidation reduction. What I was taught in high school and I teach my students is Leo the lion says grr. So Leo, losing electrons oxidized, grr is gaining electrons reduced. And it's something I even say in my head over and over again, particularly when I'm doing this unit and it's new. I'm saying Leo and grr in my head all the time. So we've got our losing electrons or oxidation with the aluminum. So the chlorine becoming chloride must be getting reduced. Now you could always go and double check. If you're in a hurry on an exam, once you found oxidation in one place and there's only one other species, you know that's going to be reduced. So we've got 0 going to -1. So 0 is picking up, or chlorine's picking up an electron. become -1. So it's gaining an electron. So that's our reduction. We can do the same thing in the second example. Here we just happen to have a ionic compound at the beginning, so we need to identify its charges. Now, copper is multivalent, so you'd want to start with the sulfur first, or sulfide first. So the charge of sulfur is always 2-. So of the two options in copper, this is the 2+, not the 1+. We've got an element in our hydrogen. We've got an element on the product side in our elemental copper, and then we've got another compound. Hydrogen is always +1 unless it's with a metal, and sulfur in a compound is always -2. So now we can identify our changes. Copper starts as an ion, becomes the elemental. So copper is, to become neutral, must gain 2 electrons. So gaining electrons, so it is being reduced. That's the copper. The sulfur is not doing anything, -2 to -2. So nothing's going on redox-wise there. So our hydrogen better be getting oxidized. 0 up to +1. So that's losing an electron to become positive. So that makes sense. So we've applied the definitions of oxidation and reduction sort of theoretically. You could always apply this to cells. No, cells are a bit more of a focus of the last part of this video series, the second outcome, but you can still apply oxidation reduction to cells. Now, voltaic cells should be treated as a much simpler example theoretically. Voltaic cells must have 2 complete half reactions, or at least standard cells. So you just need to identify what 2 complete rows do you have in your table, and you always have this table on exams. So we have a copper cell, we've got our elemental copper and our copper ion, so that half reaction is right here. Okay. And the higher up half reaction will have what gets reduced. Now our other half reaction is zinc metal, zinc ion, and that ends up being our lower half reaction on our table. Okay. And the strengths in the table is an outcome that'll come up later. There's going to be lots of mixing outcomes in this video. So the higher up half reaction of the 2 will have the best oxidizing agent and what gets reduced. So copper 2+ is what's going to get reduced, and the lower down will have what gets oxidized, and that's the zinc. So with voltaic cells, you don't need to use oxidation states to make those predictions. So that's our first outcome under general outcome 1. This video series will just be working through all these outcomes. So now we're into really a colossal outcome. As a teacher, it's like, how many outcomes do I put on a test from this particular one outcome? And it's always going to be a lot, because we're talking about OAs, we're talking about RAs in this outcome, oxidation states, which we used in the previous bit, half reactions, and disproportionation. So you should be expecting several diploma questions and many test questions. So I pulled a combustion reaction to apply some of these terms. I have a little bit of a number line, and I was using this in the previous slide. Anytime you're going up in charge, you're going to be losing electrons, and that's oxidized. Anytime you're going down in charge, you're gaining electrons, you're going to be reduced. And this little number line can be particularly helpful if you ever had a question with -4 to -5, and they're both negatives. If you can lay them out on a number line, it can help you keep everything straight. So let's figure out what's going on in this combustion reaction. We've got methane. Carbon has various oxidation states, but hydrogen, as long as it's not with a metal in a compound, is 1+. There's 4 of them. So that's +4 in total. So this must be -4 carbon. Then we have oxygen in its elemental form. So that's 0. We've got carbon again, which we need to figure out. Oxygen in a compound is always 2-, as long as it's not a peroxide, or then it's 1-. So -2 for each O. We always write oxidation states for one of the species. So the 2 of them, -2. Second one's -2, so that's -4, so we have +4. copper. And then we have water, where we just have trends. You need to memorize hydrogen is always +1 again in a compound alpha metal, and oxygen 2- unless it's in a peroxide. So now we can figure out what's going on. So we have carbon going from -4 to +4. So that'll be kind of way down here, going up to +4. So we're going up, so this is being oxidized. Our oxygen is going from 0, and we have oxygen twice, so sometimes students can get confused, but it doesn't matter which sort of pathway you follow. In either case, we're going to -2. So 0 down to -2 is what's being reduced. Now our agents are what are defined as they cause something to happen, a gain or loss in the other species. So this, our methane is being oxidized, but it causes our oxygen to get reduced. So this is our reducing agent. And we have our oxidizing agent in oxygen. And you will always find oxygen, elemental oxygen, as an oxidizing agent. So we used oxidation states. We figured out what got oxidized, what got reduced, and we've identified the agents in this combustion reaction. Sort of diving a little bit in on the oxidation states parts. This is a pretty typical, almost guaranteed question on a diploma exam of just seeing if you can identify oxidation states. And so you need to be able to do this successfully for multiple compounds to get the mark. So what are the oxidation states of sulfur in all these compounds? So we have sulfur, which will vary with oxygen. It's not an ionic compound where it's -2, so don't think ionic. In this question, oxygen oxidation state is -2. There's 2 of them, so that's -2 and -2, -4. So our sulfur must be +4. So they don't want you to key in the plus or minus, they just want the numerical value in this question. In the next one, we've got another oxygen compared to the one above. So it's still 2- for the oxygen. This is not a peroxide. Don't think of any of the carbonates or sulfates or sulfites. If something's a peroxide, it'll be clearly stated in a question. So -2 oxygen times 3 -6. So this is a +6 oxidation state. Next example, we've got hydrogen. We've got H2SO3. So we've got a few more elements to deal with to get to the sulfur. So we've got our oxygen here as -2. Our hydrogen is always +1. So now we got to figure out what the sulfur is going to be. So we've got 2 hydrogens, they're +1 each. So I'm just going to sort of keep track of things. So that would be +2. We've got our 3 O's at -2 each. So that's going to be -6. And then we need the sulfur, figure what that is, such that these all sum up to 0. So we've got +2, we got -6, so we need another 4 to get all of this to sum up to 0. Why is it summing up to 0? Because H2SO3 is a neutral compound. If there was a charge to the whole thing, well then all the oxidation states would sum up to that charge. So this is 4 again. Okay, we're not keying in the plus or minus. Last H2SO4, -2, +1. So now we've got that same +2 for the 2 hydrogens, but we've got -8 for the 4 O's. So now we need +6 for the sulfur. So that's sort of some very intro outcomes. applying this one more time, and this last question is really one that you can just use a lot of strategies to get to the answer, multiple choice strategies of eliminating some of the answers that don't connect with all the language in the question. So in acidic medium, what is the balanced reduction half reaction for the equation above? So don't even read this equation yet to kind of digest everything. So we need to have acidic. So A is acidic, B is basic, B has hydroxide in it. So B just doesn't even fit the acidic part. A is gaining electrons, so that's reduced. B is gaining electrons, reduced. C is gaining, D is gaining. So they're all reductions, so all the answers are good there. They're all halves, but A is not acidic and D has hydroxide also in it. So before we've even looked at the actual example equation given at the top, B and D are out. So we have to figure out whether it's the iodine or the ClO3 minus. So you'd be back to oxidation states. So the fastest way to deal with this is just pick one of the two pieces and figure out whether that's being oxidized or reduced or OARA. So I would pick the iodine just because it's simpler. ClO4, we're going to have to ClO3 minus, you'd have to spend some time, but iodine, this is going to be 0. And iodine on this side, let's see, we got 1 plus. For the hydrogen, we've got 2 minus for each of the 3 O's. So the 3 O's will be minus 6. The 1 hydrogen, it will be 1 plus. So what else do we need from the iodine to get this to sum up to the charge, which is 0? So we need another plus 5 for the iodine. So this is the total of the H oxidation states, the total of the iodine oxidation states, and the total of the iodine and oxygen. So we've got plus 5. So what is iodine doing? It's going from 0 up to plus 5. So our number line can always be helpful. 0 to plus 5 are going up. It is being oxidized. So this is being oxidized. So that's not what we want. We want what's being reduced. So it must be this guy. Now you could go and spend the time and double check and do the oxidation states, but there really isn't a need to in this question. It is not the iodine. It is the chloride. The last bit that I haven't touched on yet is disproportionation. So that's why I pulled out these last few examples. So don't read the box first. Always jump down to the question or sometimes scan the answers. An equation numbered above, that would be not redox. Okay, so we have to find something that is no change in oxidation states, is one of the I answers, or is the I answer, and the disproportionation is the double I. So for the not redox, we're looking at 2 or 3, 2 or 3, or 3 only. So there's no point looking at 1 or 4 as being not redox. So let's look at just 2 and 3. And now we only have to find one oxidation state change, and we know it's redox. We don't have to digest the whole thing. So very quickly, I love finding elemental forms. So potassium would be just 0. And over here, we have potassium with a charge. You don't even have to figure it out. This is clearly redox. Potassium by itself, potassium in a compound. Now it happens to be +1, both the charge and the oxidation state. So that's redox. So it should be number 3. And double replacements are never redox. Now, just because you have 2 things becoming 2 things doesn't mean it's double replacement. You have to be careful, but this is in fact a double replacement. The potassium and the hydrogen just switch places. So we have 2 ionic compounds. We do end up with a molecule and a ionic compound, but there's no change in oxidation state. Potassium is +1 on both sides. Oxygen is -2 on both sides. Hydrogen is +1 everywhere and on both sides. We've got hydrogen in 2 places, and the chloride is -1. So that's our example. That's not redox. So we're down to C or D. And now we just have to find the disproportionation. Now that is when the same species essentially atom is acting as the OA and the RA. So we have to have one atom showing up twice on the product side. Now we're looking at 1 or 4, 4, 1 or 4, or just 4. So we're focusing on the beginning and the end. Now we don't see any possibility of disproportionation in 1. We don't have a element that shows up twice with 2 different oxidation states on the product side. But we do have this in 4. We have chlorine that starts as 0, going to a oxidation state of -1 here. And we have to figure out this oxidation state. It ends up being +1. Oxygen is 2-, potassium is +1, and then the chlorine as another +1 will balance out the -2. So we've got chlorine going down to -1 and up to +1. So 4 is disproportionation. So that makes the correct answer just D. A little confusing where I circled C and D, breaking it down, but D is the final answer. So disproportionation, you're just using your oxidation state skills and looking for that same species, in this case, the elemental chlorine, losing and gaining. We've got another question around disproportionation, where we have to identify what species is undergoing the disproportionation. So in terms of possibilities, we've got chlorine at the beginning and chlorine twice on the product side, but we also have oxygen once at the beginning and oxygen twice on the product side. So we're just trying to figure out which one between the chlorine and the oxygen is undergoing disproportionation. So it's not going to be either of those products. Okay, reactants disproportionate. So I'm going to focus in on the oxygen first. It has more sort of patterns. Oxygen not in a compound, not a peroxide, is -2, and we've got just oxygen in a compound, not peroxide, -2, and in water it's still -2. So the oxygen never actually changes oxidation state, and hydrogen doesn't show up in 2 places, so that's out. So it better be the chlorine, and it's doing the same type of thing as we saw above. We've got chlorine as 0, going to chlorine here is 1 plus here, and 1 and -1 there. I should have put this the other way around. There's a few times I've been not perfect with putting my charges in the right sequence, and sometimes it doesn't matter. Charges technically are supposed to be the number first and the sign second. That is a charge. And a oxidation state, I'll just go OS, for oxidation state is the other way around. Now when you're writing these, particularly for ionic compounds, the oxidation state and the charge, they're the same thing, so it's not a big deal. You don't get tested on this. I don't test my students. The diploma won't test you on this sequence. But if you're ever wondering why there's a different order, that is why. So we're getting towards the end of this first video. One really important thing with oxidation, reduction, OAs, RAs are the trends in the reduction table. So we've got our table, it says reduction right at the top. So when you are going in the forward direction, that is reduction. Anytime you are going backwards, that is oxidation. We have our strongest oxidizing agent at the top of the left-hand column. We have our worst or weakest oxidizing agent at the bottom. So as you go up, it gets stronger. Now, as you flip to the right-hand side, we have the opposite trend. We have our strongest reducing agent. So lithium metal, elemental, is our strongest reducing agent, and the weakest, fluoride, is at the top. Now, there's also a lot of commonalities that you see on certain sides, and a few of these are really important, and I want to highlight just a few. So in terms of oxidizing agents, if something is acidic, it's always on the OA side. You never see H+ on the RA side. And anything that's basic, you always see on the Ra side, whether it's hydroxide by itself or in pairs, or H plus by itself or H plus with something like nitrate. So that's a really useful trend to know. The other maybe more important one revolves around metals. If you have an elemental metal, so you have something like copper or zinc or nickel, elemental metals are always reducing agents, no exceptions. Mostly, the metal ions are OAs, but I'm going to switch colors because you have to be careful. When you have a multivalent element and you have a middle charge, it can be on both sides. So copper can be +1, so +1 copper can be on either side. And you see this with nickel and lead. So the reds are sort of always true, really useful when we get into building reduction tables in the future. If you see a metal, you know it's a reducing agent. Okay. If you see a metal ion, you're most likely it's an OA, but slow down. You have to watch out for those multivalents. There's some few others like the chlorines, the enes are always RAs. Sorry, the enes are always OAs, and the ides are always RAs, but that one's less important. It's the acids and the metals that I think are most important trends for students. So last, we already looked a little bit into whether something was a redox reaction or not. And one big pattern is certain families are always redox or not. So we're going to end with that. So if you have any formation reaction, you have the elements with zero oxidation states. That's just always going to be true. And they're always going to have some charges or oxidation states. I will write them as oxidation states. So I put the charge first, the number second. Okay. If I wrote the charges, I just flip it around, but we always have a change here. So formation reactions are always redox. Decompositions are just the opposite. We're going to have the elemental forms at the end and the charges at the beginning. They're always going to be redox. Okay. So this can save you some time if you get is this redox? You have the same nice pattern with single replacement. In single replacement, you have to have one thing at the beginning that is in its elemental form. You can't have two, you have to have one. And that one thing in its elemental form will always turn into an ion. So a +1 oxidation state for the silver at the end. So you're always going to have an oxidation state change in single replacement. Double replacement is the one that you never have oxidation state changes. I'm just going to do a couple of the charges. I'm not going to do all of them. We have potassium, which is +1. And over here, it's just switched its partner. It's still +1 oxidation state or charge. The iodide is -1 oxidation state, and it's still -1. Okay. Something like lead is multivalent, but the lead is with 2 nitrates, -1 each. So this is 2+ lead, and it's not going to change oxidation states. It's going to stay 2+, and that's why there's 2 iodides with it. So double replacements are never redox. Now, to kind of test you or really make sure teachers do a good job teaching, they'll have some examples where 2 things become 2 things. And that might be double replacement or may not be. So watch 2 things becoming 2 things. But if you can see it's just 2 pairs of ions switching places, it's not redox. Last, we have combustion, which fits back into the always redox camp. You always have oxygen in a combustion reaction. So that's 0 at the beginning, and it's always going to a 2- oxidation state at the end. Now, O is in 2 places, but doesn't matter if there's a change, so it's always redox. Okay. So hopefully that can help you identify redox reactions really quickly. And then you don't really have to memorize anything, but you do have to be able to connect connect redox chemistry to living systems. So be it cellular respiration or photosynthesis. But you can really just apply the skills that you've learned in general to these. So I wouldn't start memorizing things. I would just apply. And cellular respiration and photosynthesis has overlap with combustions and overlap in the thermodynamics section. So hopefully you're fairly comfortable with these reactions, and you have to know about the state of water depending on whether it's open combustion or closed combustion, cellular respiration or not. So there's some overlap here with those natural processes. So hopefully this video was helpful. It helps me if you do find it useful to like the video and consider subscribing, and stay tuned for the next 3 videos in this series.